So hello again, everyone. If you weren't already in here this afternoon, my name is Tom Curran. I'm your presenter today for developing PetaLinux on Ultra96. I've been at Avnet for 12 years, working on the, and in that time I work on the Global Products and Emerging Technologies team. Most of what we do is Xilinx focused, though not all of what we do is Xilinx focused, although pretty much everything I do is. But there's, nearly a dozen people on our team that work in their own expertise areas. Mine happens to be developing training courses related to Xilinx devices, Zyng MPSOC, reference designs, PetaLinux BSPs for our development boards and our SOMs like MicroZ and PicoZ, if you're familiar with those, and definitely for UltraZ SOMs and Ultra96 board as well. And in creating those BSPs, we often need to add custom shell scripts or Linux applications, and I dabble in that as well. And that's where the fun is, when I get to do it. So an introduction to what is Ultra96, the V2 board. This is if you haven't already seen it, because it's been announced, it's been around for over a year. It is a consumer edition 96 boards form factor that uses a Zyng MPSOC device, the ZU3 EG variant device. And in the box comes the board and a 16 gigabyte micro SD memory card, a 1-year license voucher for the Xilinx SDSoC development tools. And those tools are targeted to creating accelerators in the PL hardware. So it's not just a Vivado license, it's actually an SDSoC license, which gives you a lot more capability. And a quick start card with instructions to direct you to where to go download the OS image to copy onto the SD card, and which you would then be able to boot the board. The Vivado and SDSoC and the PetaLinux tools, of course, are all available online from Xilinx. Download and license and install. And at Avnet, we provide a whole bunch of information for the board, the full schematics, the bill of materials, mechanical drawings, user guides, errata, and so on. And of course, tutorials and reference designs. And you'll all get these slides as being attendees at the conference, although I need to upload a new deck to keep it updated, because I've had to make changes. But you'll get them at this link here. So some of you were previously sitting in here for the pink session. And this is a slide you may have seen before from that session, but I'll go into spend less time on it, less detail. This is a high-level block diagram view of what a Zyng MPSOC device is, if you don't know already. Has anybody used Ultra96 or Zyng MPSOC before? Natalie has. Anybody else? So it's a combination, here we go. A combination ARM, quad-core A53, and dual-core R5 processing system, right? With our common set of peripherals that you can configure and attach directly to the processing system, like Ethernet, SPI, SD card, I2C, UART, the usual sort of peripherals. And of course, memory controller for external memory, which in this case would be DDR4 or LPDDR4. But being a Zyng MPSOC device, you also get to take advantage of a big chunk of FPGA fabric, or programmable logic, or PL for short, and the processing system we call the PS for short. So if you hear me say those terms, that's because I'm too lazy to say it. So in the PL, you can put more of the common peripherals that are attached to the PS, because that PS has a what they call the MIO, multiplexed I/O, big multiplexer attached to it that allows you to only configure a certain amount of peripherals directly to the PS. And those that you can still use but not go through the MIO mux, you have to route out through the FPGA IOs, the PL IOs. So in the PL, you can route those IOs out. Of course, being in FPGA fabric, you get to add any sort of custom peripheral, custom logic you want to or need to, and custom accelerators in the PL, like we just talked about with using Pink for custom acceleration. There's lots of other ways you can use the PL for accelerating what you would normally do in software, but take advantage of the FPGA fabric to do it much faster. So let's get into the meat of our fun here, do an introduction into PetaLinux. Has anybody used PetaLinux before? Yeah, a couple? But I'm gonna kind of generally assume that you all are Linux developers in one way or another, played with it, dabbled with it, use it every day, whatever. So PetaLinux is, essentially it's two things, two key things. It's a build system. It is the collection of open source, of course, your cross-compiling tool chain, your cross-development tool chain, your compiler, debugger, and so on. It's tailored to building embedded Linux to run on Zyng MPSOC, and even Microblaze soft processors. And of course, since about the 2016.3 version of PetaLinux, they've been based on Yocto. So it's Yocto under the covers for everything you do in PetaLinux. So if you're a Yocto developer and you're familiar with that kind of look and flow of developing Linux, then this will be familiar to you. And of course, it also includes the QEMU emulator for times when you want to boot your kernel and test your Linux image, but you don't have your hardware yet, or somebody else has your hardware and you just need to be able to test what you've done and see if it crashes or not. Another key thing to think about what PetaLinux is, it's essentially also a productivity layer. There are 6 key commands in PetaLinux that do everything you need to do. Of course, each one of those commands has lots of options, but it allows you to, if you can remember 6 key commands, then your productivity is kind of increased. So that you start off running PetaLinux-create to create your project, or install a BSP if you're starting from there. Then PetaLinux config to, of course, config your kernel, your rootfs, your U-boot, and so on. Then PetaLinux build to build your kernel, or just the rootfs, or the full image. PetaLinux boot to, if you want to boot via JTAG, then this is where you'd boot via JTAG. And then package to create a BSP of your own, to then archive or share with somebody else for further development. Or in our case, like Avnet, we package up a BSP and post it online for customers to download. They can do whatever they want with it at that point. They can continue their development with it, or just use it as an experiment, kicking the tires, testing. And PetaLinux util. So PetaLinux versus other Linux development tools. The key thing about PetaLinux is that it allows you to easily integrate what you have designed custom in the PL into your PetaLinux, into your Linux image, your project, right? Because it will import from Vivado your hardware platform, essentially, the processing system configuration, the PL bitstream, all that gets archived into a file that gets imported into PetaLinux. And part of that process is it also automatically generates the device tree based on the PS config. So it knows what peripherals are present and attached to the PS and how you're using them, which ones are used, Ethernet 1 versus Ethernet 2, SPI 1 versus SPI 2, and so on, because there's more than one for each peripheral. It automatically detects what some system peripherals, so like it'll automatically detect what SD card interface you're using for boot, and also what you're using for your system UART, your STDIO UART. Now this is to say that you can use other Linuxes to run on a Zyng device, right? Because it is, after all, ARM, right? But you'll lose the productivity enhancement of that automatic device tree generation and that automatic importing of the hardware. Other Linux tools like WinRiver or TimeSys, they can build a Linux image that runs on a Zyng device, but they won't be able to automatically integrate and incorporate that hardware platform. So it's a bit more cumbersome to use those tools to do that. Like a couple of years ago, Avnet had a relationship with WinRiver and using their Pulsar Linux, and that was a really great arrangement. But to do that, we, as Avnet, had to, and this was back in the days of the MicroZ SOMs and PicoZ SOMs, we provided to WinRiver the hardware platform and bitstream and so on, and they picked that apart and added those pieces in to the WinRiver build system so it was static. It was, what you were building was known and static. It didn't allow you to create or integrate in a custom bitstream or custom PS configuration. So it was much more cumbersome and difficult to use in some ways. But it built a Linux image that was, it booted and ran and was great at the time for that static environment. So what's included? Of course, the source code, libraries, standard Linux applications, and lots of Yocto recipes. Most of the drivers and so on are open source. There are some exceptions for some hardware drivers. PetaLinux includes and manages all the Linux kernel sources and the libraries, of course. And it includes lots of the traditional Linux applications and utilities that you're familiar with that get baked into the root file system. And through Yocto, PetaLinux makes use of being able to add additional Linux applications beyond what Xilinx supplies. And even adding more to the system of what Xilinx does supply, but not by default in the PetaLinux install. And I'll get to more on that a little bit later. So what PetaLinux builds for you? Of course, it builds your bootloaders and your firmware. It imports the FSBL it builds the FSBL, ARM trusted firmware, PMU firmware, and of course U-boot. It will create a Linux image that runs on Zyng MPSOC, and Microblaze CPUs. And for the 2018.x version of PetaLinux, it built a 4.14 kernel. The recent or current PetaLinux tools are based on the 4.19 Linux kernel. And there was something else I was going to mention there. Oh, so you mentioned there's a .x for the 2018 and 2019, and that's because Xilinx, for major release of the tools, they'll pick and standard and stay on that Linux kernel version for that entire, in this case it's essentially a year. that entire year of tool version. So for 2018, it was 2018.1, .2, and .3. For 2019.1, I believe if the last roadmap I saw, there's only going to be a .1 and a .2 version of PetaLinux for 2019. And of course, it runs on single or multiple CPUs because it's SMP Linux. It will build all of the Linux applications your system requires and spit out lots of logs and configuration files that if you're familiar with Yocto, you know exactly what all those log files look like. Some of them helpful, some of them not. And to get an idea of what your host PC is required for your host PC to build a Linux image using PetaLinux, you can get an idea of what those requirements are by looking through that user guide, Xilinx user guide 1144. And you'll find that it's not so much memory intensive like Vivado can be, if you've ever built a hardware platform in Vivado. It's more CPU intensive. So the more CPU cores and the faster they are for your Linux build system, the better you'll be. So as far as testing, release, and documentation go, for the U-boot and kernel and Xen hypervisor side of the build, of course, it's all built from kernel.org sources plus what Xilinx creates on their own and patches that they add to the kernel. For testing, Xilinx will do their testing on, of course, on their devices and on their development boards to test to make sure, of course, that the device behaves as it should and that the features of the board are usable as a user would expect them to be. Documentation, of course, is all source code and online resources like community forums and so on. And Xilinx occasionally will publish an answer record if a significant bug comes up that and a workaround is known. They'll publish an answer record to direct customers. Hey, we know this is an issue. This is what you need to do to work around it, or whatever to do about it. On the file system side of the build, all the sources come from the Yocto community code base. All the testing is done simply by doing a build verification, make sure everything compiles. And Xilinx will test out anything that they've built themselves and added to PetaLinux, whether that's special applications that are board specific, like we'll see for Ultra96, or anything like that. And release strategy for the file system is really based on how quickly Yocto goes through its update cycle. Right? And the same sort of documentation, source code and online forums, open in communities. So a Zyng MPSOC device, like I say, it's your quad ARM A53 processing system. So it boots Linux much like any other processor. Slightly different though in the fact that when the device boots up, when the device powers on, it doesn't yet immediately know what its boot method is. So one of the first things it does is it samples the boot mode bootstrap pins on the board. And in this case for Ultra96, it determines because that switch can either be set for JTAG or micro SD card. It's going to sense, oh, I'm booting from SD card. I'm going to go fetch the FSBL from the SD card, which is buried in the boot.bin file. And it knows what to do with the boot.bin file. It's going to load the FSBL into on-chip memory and execute from there. And it runs from OCM because one of the things the FSBL does is it configures the memory controller and the rest of the processing system for what peripherals are also present and where they're located in that MIO mux and what their settings are, some of their settings are. Then the PMU firmware and ARM trusted firmware get loaded, right? And in this case, for the Ultra96, we have a customized PMU firmware that's been modified to handle the push button power switch that you have on the Ultra96 board that takes care of shutting down the OS gracefully before powering down the board. And then it will load U-boot into external memory and hand off execution to U-boot. U-boot does its thing, right, and then loads the kernel into memory. And if it's a small, simple system, this Linux image will also include the root FS as a RAM disk. So that'll be loaded from external memory also. So then U-boot hands off execution to Linux, and then Linux finds its root file system and continues booting. So the main difference here that you'd find from other, I'm guessing you'd find from other ARM SoCs is the FSBL. Your PetaLinux tools flow, and you're creating a project, building a project, and so on. A couple different ways to start. You can start completely from scratch, ultimately in Vivado, to create that processing system configuration, essentially the hardware platform. If that is something completely foreign to you that you don't know and don't want to know anything about, you can start by getting a BSP from someone like Avnet that allows you to start from a known good project, PetaLinux project, and continue to customize it, build it, whatever you want to do with it. So a couple different ways to start. Once you've either created the project from scratch or installed the BSP, you then run through PetaLinux config. And the dash config is also, if you have started from scratch, it's where you will import your hardware platform specification from Vivado, right? And from there, you config the kernel with any extra kernel settings you want to modify or change or add. A common one that gets forgotten to add is SpyDev or I2C. Because even though that I2C peripheral is in your hardware, Linux doesn't automatically know about it. The Linux config doesn't automatically know about it. So you often have to go into the kernel config to make sure that those are added to the Linux build. From here, you also config the root file system if there's anything you want to add or change about the file system config. And the same goes for U-boot. Once you're done configuring, you move on to PetaLinux Build, and you can build each component at a time. If, say you're developing an application and you don't want to build the entire system just to test if your application will build, you can specify the name of the application or the kernel module that you're building and build just that. But without specifying any options, you run PetaLinux Build to build the entire image. And this is also how you clean it, because there's a command line option to clean the project from either going all the way back to square one, like a clean slate using Mr. Proper, or dist clean to just partially clean things up. And then from there, you're ready to boot. Boot it, test it, see if it crashes. Hopefully it doesn't. And go through the iterative process to decide, okay, make sure that it includes everything I need, make sure that everything's configured the way it's supposed to be, make sure I've got the right applications in my root FS, and so on. And then package it for either archive for posterity or for handing off to someone else. So this gives you an idea of what PetaLinux looks like when it's installed. Not that you ever need to go in and change anything in there, but it is sometimes helpful to know what is where in the PetaLinux install folders. And also, more importantly, what is where in your PetaLinux project folders. So those of you that are familiar with Yocto, this will look very familiar to you, or the common set of folders. But what it really comes down to, everything you want to touch, everything you really can touch without changes being overwritten or without causing other sorts of problems, is under the meta user folder. This is configuration files, recipes, lots and lots of recipes. Anything you create as a module or an application or a shell script to be added to the system gets created and added as a recipe. And the rest of the project is just the binary images for the kernel image and U-boot and so on get in the images folder. Anything to do with all your build logs, compile logs, and so on, they're in the build folder, buried deep in the build folder. So anything you want to touch is going to be in those folders. So PetaLinux and Yocto. PetaLinux, of course, supports and is supported by the Yocto ecosystem. There are people at Xilinx that are very connected within the Yocto, what do you want to call it, developer community. PetaLinux has the ability through through recipes, creating and adding recipes, to integrate Yocto-generated feeds into the PetaLinux build. The root file system you're going to build. So this allows designers to fully leverage what the Yocto community provides. The Yocto build system generates the full PetaLinux file system, right? So this ensures that all the Yocto built software is library compatible with Xilinx provided software, and of course, being Yocto and being very Git centric allows for comprehensive revision and source control. And Xilinx provides Yocto recipes for all the PetaLinux components: the kernel, the PMU firmware, the ARM trusted firmware, and of course the root file system. Everything is based on recipes. So more about those recipes: PetaLinux and Bitbake. Because PetaLinux, think of it as a productivity layer. Those 6 key commands that I mentioned that have all the different options to them. Underneath all those commands are all the Bitbake commands abstracted for you, right? So Bitbake commands can sometimes be terse and a little cryptic, hard to remember when you're using them. PetaLinux command abstracts that sort of detail for you, kind of enhances your productivity when doing your Linux builds. So the commands, like from creating a software application or kernel module, or simply if you want to add a handy shell script to your file system, you create recipes for that. The command, like a PetaLinux create modules command, will create everything for you. The recipe, the folder that it gets put into under meta user, a make file if it's an application, the recipe itself, and even a stub, a sample source file, right? All of which you then go further edit, but the structure of what you need is there, created for you automatically. You don't have to do it yourself. And you simply, edit the source files and make files and so on as you need to. So here's a sample of a PetaLinux build command to just build the rootfs, right? to do it in Bitbake is a more complex command, more typing. And if you type like me, that's just more errors to make and backspacing. So we've gone through the introduction to PetaLinux. Now let's take a look at the anatomy of a PetaLinux build, what you'll do when you actually build your own PetaLinux system. Like I said, we'll start off by using running the PetaLinux create command, and we're either going to create a project from scratch, which will then later import our hardware platform from Vivado, or hopefully we'll just grab a BSP from Avnet and use that as our basis for our development, right? Start with something we know is good and we know will work. So different options you have are to specify the type. -T can either be the project or an app or software library that you're going to build for yourself, or a kernel module you're going to add to the system. Perhaps for Wi-Fi, as we'll see a little bit later. If you are building completely from scratch, then you'll use the PetaLinux config command to import that hardware platform specification from Vivado, like I mentioned, simply by using that long option right there, and specify the path to the source of that hardware platform. You'll also use this command, like I say, to config the project itself, config all the build components, U-boot, kernel, and so on. Now, you'll almost always, at least I find, I almost always want to extend the root file system in some way. And because we're based on Yocto, the key way to do that is navigate through your project folders, meta-user, recipes core, blah, 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 to PetaLinux image full.bb append file. And this is where you get to manually, unfortunately, add packages, and in this case, packages that Xilinx provides, although they don't provide them by default in the PetaLinux install. But they provide package groups of applications and utilities that the Ultra96 board requires for the out-of-box image, anyway. For the web application, video for Linux utils, applications and configurations for the sensor mezzanine that can be mounted to the Ultra96 board, X11 windowing environment, X11 for the graphics, and then Matchbox for the windowing environment. And you'll see that when you add these lines to the BB append file, you then will see these configuration options in your rootfs configuration, right? Which you can then enable or disable as you want to. And then you're ready to build, right? Just you can, like I said, you can build each component individually or build the full image all at once. And of course, building the full image all at once is going to take, depending on the complexity of the system and the rootfs, the complexity of the rootfs adds more, is where a lot of the time gets spent in the build time. The simple rootfs builds much faster than a complex one, a more sophisticated one like we have on the out-of-box for the Ultra96 board. So we've gone through the steps of what you'll go through to build your own PetaLinux image, right? The commands and how you'll use them. But now we want to look at, it's not just a default Linux image that we want to build and run on our Ultra96 board. We need to integrate a custom device driver. And that's because in the migration from the original version of the Ultra96 board that used a TI, Y-Link 8, Wi-Fi, and BLE module, to make it more Avnet friendly globally, we replaced that TI module with a Wi-Fi and BLE module from Microchip, what they call the AT WILC, W-I-L-C, 3000 actually. And we did that one, like I said, because it's more friendly for Avnet globally, and because it is certified in more countries globally, like 75 countries globally. So that makes it a lot easier for Avnet to sell in more countries globally. But as great as this module is, Microchip, of course, only tests it on their development boards and their ARM SoCs. And all of their ARM SoCs are either Cortex M0 or M4 based, right, which is a different architecture than the Cortex A53s that we have in the Zyng MPSOC. So that's not to knock Microchip, right? They're playing within their sandbox. They're doing what they do best. They create this driver, but it's Avnet that is kind of like pushing things a bit further to use this module on a different class of ARM device, ARM CPU. So what we found is that the correct driver that we needed isn't in mainline. There is a WILC driver in mainline, but it's just not the one we can use. So, and to Microchip's credit, they continuously develop the driver to keep it up to date with latest kernel versions, right? So that's good. Right? It's not just something that's sitting static in some GitHub repository somewhere. It is continuously being developed. But that meant we also needed to create a custom recipe to pull the correct driver. But we also needed to take that a bit further to customize it for the Ultra96 board because of those differences I mentioned between the ARM v7 and v8 architecture. We also found that the driver as Microchip provided it, it would go out and fiddle with the power management while the device needs to fetch an IP address from a DHCP server, and that created a stability issue, and the board would often crash. Right? The kernel would often crash, which is obviously no fun, right? And no good when you're trying to create a solution for customers that you expect to be stable and you want that Wi-Fi to be usable because that is the primary means of internet connectivity and LAN connectivity. And we also had to disable, the driver had a way to manipulate the module enable and reset pins, which could be set up either via source code or via the device tree. But to get the driver working reliably, we had to disable this driver manipulation of those pins. So this is edits that Avnet has had to make. So that means now that we have forked off the driver sources into our own GitHub repository, and that involved lots of collaboration and email threads with Microchip, and we are working with them to now, because we needed to move a little bit further than they could to get this solution done and get this board shipped for customers to buy and use. So that means we now at Avnet will work with Microchip to get our changes pushed upstream to them, and then it's up to them to push upstream even further to mainline as they see fit. Right? And that's part of that bubble that was talked about this morning. Why don't SoC vendors push up, do more pushing upstream? Lots of reasons why. So in creating this custom kernel module, a few key things to do. Run that PetaLinux create command, specify the type as a module, give it a name, and enable it to be included in the config menus. Right? key line in the recipe is to specify the source of where the sources live, because we don't keep them local. We don't want to do that. We want to leverage GitHub, leverage Git, revision control, specify where the sources live, and that we'll use the HTTP protocol to fetch them, and we want them from the v15_2 branch of that repository. And even further, we specify the source rev by giving the git commit of the specific set of files, for the specific set of files for our driver sources. And then a little later on in the recipe, we get to specify some make and config. No, like these lines here, config wilk. These would normally be in your kernel config, but because we're not using the kernel config, we're using this custom recipe, we specify them here, right? We tell the build that it's a module. We specify some options that it's not using the hardware out-of-bound interrupt, things like that. The sorts of things you can add to a recipe. So we've built our system, integrated that custom driver. We've seen how we can use PetaLinux to increase our productivity, because it is our productivity on top of Yocto, essentially. We at Avnet have taken that even a step further. We've created the GitHub, Git repositories for PetaLinux and Vivado build scripts. And here are the links there. The BDF, if you're familiar with Vivado, these are the board definition files. So Vivado is board aware of what board you're targeting. Ultra96, MicroZ, PicoZ, UltraZ, and so on. Or if you're targeting a Xilinx board like ZCU111 or ZC702 or something. Those board definition files are required by Vivado that we use in these HDL scripts that are in the HDL repository. And of course, our PetaLinux scripts are in the PetaLinux repository. So you'll need all three of the repositories, and you'll need to clone them into the same parent folder, because the scripts rely on relative paths to the other repositories. So they need to be under the same parent. And you'll also need to, if you're building for PetaLinux 2018.3, you need to make sure you check out the branch. And the PetaLinux and Vivado branches need to match. So if you're building for Vivado PetaLinux 2018.3, you'll need to make sure you also check out the Vivado 2018.3 branch from the HDL repository. So why use build script to build your BSP? Main thing is the build scripts really help to automate the steps to create and recreate and build the BSP. So for us, that means we get to avoid the problem of it gets confusing. What I do today to build the BSP, I'm going to forget when I need to rebuild it for the next version of tools, or if I need to make a small change later, right? But if it's scripted, I don't need to worry about that. That script is always going to do the same thing every time I build. So and I'm using Git, so I get to track any changes I make, and it's all source controlled. This makes it easy for us to update BSPs from one tool's version to the next. Sometimes this is really very simple. Other times things break between tools versions, especially major tools releases like from 2018 to 2019 and so on. It also allows us to build mini BSPs at once. So for boards that have different variants, like a MicroZ SOM or a PicoZ SOM, there are 4 different PicoZs. So we want to be able to, that's 4 different BSPs we need to build, and different boot binaries we need to build for, because each SOM has different boot methods, whether it's quad SPI, eMMC, or SD card. So it allows us to build all of those at once, like set it off at night and go to bed and come back the next morning. And it also allows you to create, the script itself can write out the file for other scripts that are handy to run for booting from JTAG, which, a combination of JTAG and TFTP, which TFTP for smaller systems that like use a RAM disk is so much easier than always copying files to an SD card every time you want to make a change to what you're booting. TFTP is really slick for small systems. And of course, for quad SPI and eMMC programming, it's really handy to just have that script to take care of that task for you. So here's a brief excerpt from one of our build scripts, this one for the Ultra96-V2, where we, like I said, many of our SOMs and boards have more than one boot method, so we need to specify the boot method. In this case, it's an SD card. It's going to have the root file system is going to exist on an ext4 partition. We'll need to specify where the PetaLinux and Vivado tools live. And I didn't mention this before, but I think I need to now, that you don't have to know anything about Vivado, the hardware tools, to build the PetaLinux BSP using these scripts, because the PetaLinux script will go out and look for that Vivado hardware platform. And it knows where to look because we specify where the input files can be found, right? And if it doesn't exist, then PetaLinux, this build script will call the Vivado tools to build that hardware platform for you. So you never have to touch Vivado. It'll be taken care of in the background, right? So the build script needs to know where you have the PetaLinux tools installed, because it needs to set environment variables, right? So it knows where the PetaLinux and Vivado executables can be found. And then we also specify what version of tools we're using, the name of our FSBL, and what we want the name of our PetaLinux project to be. So like I said, the first thing that the build script will do is it will go out and it will source the tool settings. And because we've told it where those tools are installed, it knows where to go grab the shells, to go run the shell scripts to set the environment variables that need to be set in order to run the tools. Beyond that, next step it does is, if it doesn't already exist, it will build your Vivado hardware platform that is the underlying hardware platform that your Linux will run on. And if it already exists, then it just skips that step. The next thing it does is it creates the BSP, and it runs all those commands to create, config, import, it'll create the device tree, build the rootfs and the kernel and U-boot and all that. Builds all of that for you automatically. And we'll package up the FSBL and the firmwares and U-boot, and if there is one, the bitstream. It'll package that up into a boot.bin file that is needed on the SD card for booting. And then we'll package up everything into a BSP that you can then archive or pass off to someone else. Or for me, work for Avnet, you then put it up online somewhere for someone else to download later on. So that's the end of the meat of the presentation. Now I get to throw a lot of web links at you. Don't expect you to write these down. Like I said, you're going to get these slides, so these will be handy for you later. These are important links and information that we found really helpful. There's the technical training courses I mentioned. Some of them are available on demand. download the BSP to download, documentation. Adam Taylor has created these, if you're familiar with him at all, has this long ongoing MicroZ Chronicles sort of blog. Often it's a video blog or videos involved, but he runs through the two methods of building PetaLinux for Ultra96. So that one's really interesting. You get to see different methods of building PetaLinux. And last year, this is my course from Xilinx Developer Forum last year of doing application development on an Ultra96 board, right, with Linux running, so using the Xilinx SDK and tools to build an application. Other helpful resources, there's those Git repositories I mentioned. All the work that we do at Avnet, we do in a virtual box, virtual machine for our Linux development. We have found that it's nice for our customers to provide a tutorial sort of document that walks you through all the steps needed from beginning to end to create the virtual machine, install the tools into it, set that up as a development environment. So we publish that online. These are two crucial Xilinx user guides, the PetaLinux documentation reference guide and the command line reference guide. So everything I described about the commands and their options is all in user guide 1157. Everything else about PetaLinux is in user guide 1144. So you'll want to know those and where to find them. And that's all I've got. So any questions? Yeah.
Going back to the custom driver for the Wi-Fi, that command line assumes that driver's already been upstreamed into the kernel.org, and that's the actual kernel image that you're pulling down.
Not necessarily, because you can, like we did, we specify where to find the kernel sources in the recipe, where to find the driver sources in the recipe.
Okay, so it's actually going to build it in for you then.
Right.
Okay.
Right. So it builds it as a .ko file, and then I don't show it here, but in the running Linux image, there's a script that runs that loads the module and then brings up the Wi-Fi interface. Yeah. You just grab the microphone from...
This is a little bit out of scope, but I'm curious, do you have any examples of also making use of the R cores on these devices? Because that's of interest to me to have the A cores and the FPGA fabric. But I was also interested in getting Zephyr running on the dual R cores on these boards.
That we don't have right now.
Okay.
That may be something we do in the future.
Okay, it's a bit out of scope for things like sensors where I need to pull data in at a very fixed rate to be deterministic.
Deterministic?
The R core is sort of essential in that respect.
So you're looking at like doing an open amp sort of?
Yeah. That's I was just curious. I mean, it's on my to-do list anyway to get the R cores working. I'm just wondering if there's any head starts on
I wish I could say yes,
okay, well.
but right now I know I don't have a head start.
The situation anyway.
Yeah.
Okay.
But that comes up from time to time, so that's a good feedback for me to throw back at my boss. Like, this is something.
There's two of them sitting there that aren't getting used.
Yeah, in this system, they're idle.
So on the Zenboard.org website, there's some content on there. It's fairly old. It's from 2016.2 that has an open amp design that I can share with you. But yeah, it's old. Just fair warning.
Also, Ed Mooring from Xilinx, who does OpenAMP. Oh, okay. Okay, so if you've had a chance to meet him here, then he's a good person to talk to, maybe.
In one of the slides, you have shown that graphics is part of PL, PS, and video is part of PL. And if we want to access both the modules at means if I'm developing an application which needs to use both graphics as well as video, so in that case, what kind of user interface is opened up by this SDK? Because as I understand that this platform will compile all the kernel modules.
Yeah.
It will include your Matchbox for the graphics and
Right.
B4L utils for the video.
Right.
But that will be at the kernel level. But when you go to the user space for the app development, so what kind of interface it opens? Or what kind of interface is available for app development?
Well, they'd be APIs provided by the kernel. But I've never written an application for video. But there are frameworks like Qt
Okay.
that you would use for doing a thing for doing.
So is there any example for such kind of usage you have?
Not that we have, but I have seen it, and recently. Where was that?
Like for
I
example,
think that might have been on Hackster.io. Somebody used developing with Qt on the Ultra96 board. So if you go to Hackster.io, you'll find it,
Okay.
and they're usually pretty good. Like people out in the community doing some really fun and interesting stuff like that.
Hex.io.
Yeah.
Okay, sure. Thank you.
Anybody else? All right. We're done. Thank you.